My name is Arjun Raghuraman, and I work for the Dow Chemical Company as a process technology leader. Today, I'll talk to you about ways to leverage the multiparadigm capability and nature of the Wolfram language to solve problems in polymer reaction engineering. The talk will cover mathematical modeling of polymerization reactors using the deterministic approach, which is based on first principles. And the polymer of interest are polyether polyols, which I will introduce in the next slide. Here is a graph showing the high-level approach that is taken. It essentially involves creating a population balance from an assumed reaction mechanism. And this population balance is a system of mathematical equations that tracks every chain in the polymerization reactor, along with monomer, and in a way that is consistent with the reactor configuration. Solution to the population balance leads to the full molecular weight distribution of the product, from which several useful properties can be computed. Polyether polyols are polymeric intermediates to polyurethanes, and they're made by ring-opening polymerization of epoxide monomers, such as the one shown here, which is propylene oxide. These are often star-shaped structures with multiple arms, and an elegant approach to modeling these polymers is to first solve for the single-arm distribution and transform those results to multi-arm structures. I've shown you 2D and 3D representations of single-arm structures. Here, the highlighted atom in yellow represents the initiating end, and the OH group represents the chain end. There are at least 4 paradigms in the Wolfram language that I find to be very useful to tackle problems like these. The first is symbolic tracking of polymer chains. The second is in the paclet repository, where there are functions that make the creation of these population balances very efficient. The third is in all of the numerical mathematics capabilities, because more often than not, these kind of models are implicit, and the only possible solution is one in which numerical integration of a system of differential equations or numerical root finding of algebraic equations is the only possible solution. There are several functions in the core language as well that can be leveraged, such as built-in parametric distributions for initial guesses, as well as parallel computing capabilities, which become exceedingly important when there are long chains in the reactor, which means a great number of mathematical equations. The symbolic nature of the Wolfram language is definitely well suited for application in polymer reaction engineering, and it offers considerable flexibility. For example, P of I can represent the molar concentration of chains with I repeat units, and this makes it possible to use functions like table to quickly generate symbolic representations for all species in the reactors. An extension of this is P of I, J, E, which can represent the molar concentration of chains with I repeat units of monomer 1, J repeat units of monomer 2, and N group E. Finally, in dynamic or unsteady systems, the concentration of polymer chains varies with time, and P of I of T can represent the molar concentration of chains as a function of chain length I and as a function of the independent variable time. Before I get into mathematical modeling, I'll first discuss the underlying chemistry, and will focus mostly on anionic ring opening polymerization. But towards the end of the talk, I will mention coordinative polymerization as well. In the initiation step, a catalyst like KOH is added to an alcohol or a polyalcohol to convert a fraction of these OH groups into the alkoxide group with removal of water. And this step is usually done in a separate reactor, and the product is stored. Therefore, in the models that I will show you in the next few slides, I will not discuss the kinetics of initiation. The propagation step is critical. This is the molecular weight building step. Here, the alkoxide chains with alkoxide end groups attack the monomer. Organic chemists love to push arrows. So I'm showing here an arrow from the nucleophilic oxygen to the less hindered carbon on the monomer with breaking of the CO ether bond to give you the product. Based on the symbolic representations I showed in the previous slide, this structure can be represented as P of 3 because there are 3 propylene oxide units and the product would be P of 4. Chain exchange or chain transfer to polymer is a reaction where there is fast proton transfer. So for example, an active chain P of 3 can abstract a proton, but it can do that from any one of several dormant chains with neutral OH groups in the end. When P of 3 abstracts a proton from any of these chains, it becomes the dormant chain D of 3. For more information on the chemistry of anionic ring opening polymerization, here are some references if you want to read up on that. Chemical reaction engineers often resort to macroscopic balances based on conservation principles to obtain high-level information about chemical systems. The general mole balance equation is based on the conservation of mass, and it can be applied to any polymerization reactor. The notation I've used is the same that Professor Fogler's used in the book Elements of Chemical Reaction Engineering. So here Fj0 represents the molar flow rate of species J into a reactor of volume V, that is shown by this red spline curve. Fj is the rate at which the species is removed from the reactor. Gj is the molar rate of generation of that species due to chemical reaction, and the unsteady term is written as dnj over dt, and that represents the rate of accumulation of species J. So by the conservation of mass, the general mole balance equation takes this form. And in the next few slides, I'll show you how this is applied to different types of polymerization reactors, such as the batch, semi-batch, and the continuous stirred-tank reactor. For well-mixed batch reactors, the general mole balance equation, or GMBE, takes on a simple form where the rate of generation of species J equals its rate of accumulation. V is usually held as a constant because the assumption is that the density of the reaction mixture can approximately be treated as a constant. We now load the paclet from Robert Nipbar on compartmental modeling. Here, Nmax sets the truncation limit of polyol chains. In theory, one needs an infinite number of equations for a polymerization reactor, but practical implementation often involves setting a truncation limit without significant loss in accuracy. This kinetic compartmental model function is very useful because it can accept symbolic reaction representations, such as the two shown here. Here, I've specified 2 reactions, the propagation and exchange reaction that I showed in a previous slide. In the propagation reaction, a chain P of I reacts with monomer and extends to P of I plus 1, and the table function is used to iterate over all values of I from 0, which represents the initiator, to the truncation limit. In the exchange reaction, an active chain P of I abstracts a proton from a dormant chain and becomes a dormant chain D of I. And when that happens, the dormant chain D of J becomes the active chain P of J. And again, this is iterated using table over all values of I and J from 0 to the truncation limit. Note that just in a few lines of code, 103 mathematical equations can be generated corresponding to this specific system. There are 103 equations because there are 51 equations of P from 0 to the truncation limit. There are 51 equations for D, the dormant chains, from 0 to the truncation limit. And there's 1 equation for the monomer M. The polymerization reactors run for 4 hours, and the model is written as a function of 2 parameters, theta 1 and theta 2. which correspond to the propagation rate constant and the exchange rate constant. Note that the equations and state variables can be conveniently extracted using associations. So to plot the results, I first drop the first term in the solution, which corresponds to monomer. The rest of the terms correspond to chains, which is what we're interested in. And then the solution is called at the final time of 4 hours. And the active and dormant chains are totaled for every chain length in the system. I've done this for 2 cases, one in which the exchange rate constant is significantly higher than the propagation constant, and in one in which they are approximately similar order of magnitude. Here are the results which show that when this fast exchange, which corresponds to this first case here, a narrow molecular weight distribution is obtained, and that fits well with the Poisson distribution. When the exchange is slow, the distribution now broadens. And this is a well-known result in the field of controlled or living polymerization where there's no chain termination. In a well-mixed semi-batch reactor, monomer M is fed into the reactor at a controlled rate for safe operation. And these are common in industry for exothermic reactions, but mathematically they are more complex. The monomer balance then takes a modified form to account for monomer feed into the reactor. Here FM0 is the molar feed rate of monomer into the reactor, minus GM is the rate of consumption, and that's the accumulation term. For polyol chains, no chains are fed into the reactor or removed from the reactor typically. So the balance resembles that shown for the batch reactor in the previous slide, except that V is now a function of time. So we need an extra equation to specify that. And in this case, the compartmental modeling paclet cannot be directly used. So I used replacement rules to modify the original equations for the paclet, and I've shown an example of that here. The semi-batch model again is written as a function of 2 parameters, theta 1 and theta 2. But here I extract the left-hand side and right-hand side of the equations and modify them to be consistent with the monomer and chain balances that I showed you in the previous slide, and then just thread them together. Note that the feed rate of monomer into the reactor is specified as a piecewise function, and this is a simple case where the feed is constant for a certain duration, and that's 16 hours. And then the feed is dropped to 0 for an additional 2 hours, and that's typically called the digestion time. The model results are shown in this plot. The results for the distribution is essentially identical to the batch reactor, but the monomer concentration profile is significantly different. And there's a constant unreacted monomer concentration for the duration that the feed is constant. And when the feed drops to 0, you see a digestion which resembles that of a batch reactor. Copolymers are also complex systems. For now, I will only discuss copolymers in batch reactors. As mentioned before, P of I, J, E can represent the molar concentration of a chain where there are I number of repeat units of monomer 1. In this case, that's propylene oxide. And this is independent of how it's distributed in the chain. So what we are tracking here is the overall number of repeat units of monomers 1 and 2 in the chain. And we're not paying attention to the sequence of that monomer. E can only take on 3 values, 1 for PO ends, 2 for EO ends, and 0 for initiator ends. I set a lower truncation limit just for illustrative purposes, and the polymerization batch reactors run for 20 hours. Here I'll discuss the symbolic representation of reactions that are given to the kinetic compartmental model function. P of 0, 0, 0 represents the initiator. And I've chosen to include the number of repeat units of monomer 1 and 2 within a list just to make it convenient and more easily readable. when the initiator reacts with the first monomer PO, you now have PO ends. So this index E takes a value of 1, and the number of PO units is now updated from 0 to 1. Similarly, when the initiator reacts with the second monomer, the ends are different, so it gets a different value of the index. And the number of repeat units of the second monomer is now updated and increased from 0 to 1. And this is now carried out for all possible combinations in the system, and it's conveniently done using table. Note that in this case, table is iterating both I and j from 0 to the truncation limit. In my workstation, it took about 15 seconds to generate all the information for the model. And the number of equations for the specific system is 1355. I'm directly showing you the results, which is a symmetrical copolymer distribution. And that's only because I set all of these rate constants to be equal to each other. Finally, we look at a continuous stirred tank reactor, but only at steady state operation. In this case, the accumulation term is set to 0, and then the system reduces to algebraic equations, and the paclet cannot be used for this specific configuration. So I hard-coded all the equations into the model, which I will show you in the next slide. And find root now is used to solve the system, where the initial guesses were derived from these built-in statistical distributions in the core language. And it's great that there are so many distributions that are available for researchers like myself, and it makes it convenient to model. The model is written as a function of the truncation limit. And then in this specific case, the initial guesses come from a Poisson distribution, and it's passed on to find root to find the solution to all these algebraic equations. And here I plot the results. Note that even though the chemistry is the same, the molecular weight distributions are significantly broader in a stirred tank reactor. And these are the kind of things that are very interesting to a chemist like me, to see how reactor configuration plays a role in the product that you make, mathematically and computationally. And note that in this case, the truncation limit of 25 is insufficient to model the system, and it has to be increased to 100 so that the probability of finding a polyol is 1. For the last part of my presentation, I'll discuss an entirely different catalyst called the double metal cyanide catalyst, and this offers an interesting example. The catalyst is heterogeneous in nature, so the precise structure is unknown, and I've shown you a structural representation. The active catalyst has extra zinc relative to these cobalt atoms. And what you're seeing here is a hexacyanocobaltate framework that is extended by zinc atoms. And this cyanocobaltate framework is chemically stable. It supports the placement of extra zinc within the structure. And it is thought that these extra zinc sites, which are unsaturated, are the active sites in the catalyst. And there are several empirical observations that are interesting. One is that the catalysis is selective for shorter chains than longer chains. And so in all of the previous examples that I showed, the assumption was that the propagation rate constant was independent of chain length. That's no longer the case for this kind of catalysis. The catalyst is inhibited by high concentrations of shorter chains. And we found that a classical Landmeyer-Hinchelwood mechanism is insufficient to explain the unusual behavior of the catalyst. In this kind of mechanism, one can imagine that a vacant zinc site can bind a monomer to form a complex, and if there's an adjacent zinc site within about 10 angstroms from the monomer-bound site, that site can bind a chain, and this sets up the environment for ring opening and polymerization to take place. But the observed behavior is more complex, and there seems to be two regimes, one in which the rate is proportional to the concentration of OHs for long chains, and there is a 1/x relationship for shorter chains. And we developed a mathematical model for this catalyst, and I'll show you the results of that model. I'm not able to get into the details because that's proprietary, but the results are interesting, and it shows that even in a continuous stirred tank reactor, one can narrow the molecular weight distribution of these products. And this caused a transformation in my industry over the last decade or so, because until that point, the chemistry was done in batch reactors to get narrower distributions, but this catalysis enabled continuous manufacturing for certain products, and that led to an improvement in productivity. And one explanation behind this result is related to the heterogeneous nature of this catalyst. In KOH catalysis, the K plus can easily find the ends or dominant chain, whereas in DMC catalysis, the chain has to find the catalyst, and the probability of doing that is related to the volume of this random coil of chain that is shown here. And for the chain to find the catalyst, the growing end has to find the surface of this sphere. And the probability of doing that is higher for shorter chains. And that is why we think this catalyst is more selective for shorter chains. So to conclude, the multi-paradigm and symbolic nature of the Wolfram language does offer a powerful platform in polymer reaction engineering applications. And I do find the compartmental modeling paclet to be very useful, and it simplifies the mathematical representation of these systems. Expansion of this paclet to accommodate well-known reactor configurations is recommended, and the population balance methodology described to solve the reaction system can get limiting when there are longer chains in the system or when there are comonomers, and this is where the parallel computing functions alleviate the problem to a certain extent, and it's very good to see continued development of these parallel computing capabilities in the Wolfram language. I'll finally conclude with some acknowledgements. Carlos Villa is a former colleague of mine who retired from Dow. He's been a mentor and instrumental in my journey in polymer reaction engineering in general, and in my use of Mathematica. I'd like to acknowledge the Polyether process R&D group and all my teammates at Dow. I'd like to acknowledge Wolfram's support, especially Robert Nakbar, Louis Breton, and Seraphine Covenant. And a final thought is, I'm trained as an organic and medicinal chemist, and Wolfram has been instrumental in blurring the interface between chemistry and chemical reaction engineering for me. And being able to speak both languages is highly beneficial in industrial research. So I've shown this thematically as a bridge that represents chemical reaction engineering, which connects chemistry to manufacturing. And I put spiky here because that's the interface that is important to me.